So type of flows, let's talk about turbulent flow, which is very important in engineering applications. We expect high velocities, a lot of chaos. We expect a lot of whirlpools or eddies, as they are known. The wall effect is so small. So for example, in the laminar flow in that section, we saw that this should be 0 velocity because they are stick to the wall. But in turbulent flow, this is almost negligible, like nothing. You can ignore this because all this will be in a very chaotic way. Plug flow in many cases may be used. We're going to see that later. And Reynolds number must be larger than 10 to the 5 power. So that is something like 100,000. So if you have something less than that, but more than 2,000, you will be in a limbo region. To calculate the minimum speed needed to achieve turbulent flow given this density of the fluid, this viscosity of the fluid, and this pipe diameter. And I love this exercise because it's very straightforward. You have this pipe, you have a fluid which is known, you know the density and the viscosity won't change. The pipe is fixed, so you cannot move the diameter, and they will tell you what is the minimum velocity to achieve turbulent flow, because we want to work in turbulence. So you go here, calculate, you have your Reynolds number, you go to density, velocity, diameter, and so on, substitute everything, and you get this value right here, which is relatively high compared to the other value we got here. This was 0.015, this is 0.66. Good. So guys, now let's suppose we change the diameter, which is kind of common. Imagine we had this was 0.20, which one? 20 was 25, and then it goes triple to 75. Okay. Let's assume same density, same viscosity. Therefore, if we suppose the velocity, the minimum velocity must be this one right here. So we have this Reynolds number, we have this density, we have this viscosity, and this new diameter. So you will probably ask yourself, how can you have a lower velocity compared with this one right here, which was 0.66 meters per second. And the interesting part right here, guys, is that actually you need to change the flow rate, because flow rate is velocity times area. The area depends on the diameter. Since we are changing the diameter, it means we have more area, and means that if we lower the velocity, we will change the volumetric flow rate, which was right here. So for example, we have Q1, we have Q1, which will be the one with the velocity of 66 times the area with the diameter of 25. So right here. This will definitely not be the same as this volumetric flow rate right here, which let's call volumetric flow rate 2, will be the velocity of 22 and the area of 75. You will see that this number won't be equal to the one on here. So what means this is that you cannot operate this system because they are not the same. So you will either have to change the flow rate, or these are separate pipes. This was a free preview. You want to get full access, go to my incompressible flow course. The link is in the description of the video. You will get all access. Not only that, you get a very straightforward, user-friendly interface. So for instance, if you were analyzing or studying pumps, you have it here, the pump block, and then you have the sections. If you're, for example, studying the types of pumps, you can go here, and you have all the classes right here. Not to mention that you also have introduction and conclusion of every one of these. So for instance, if you were studying positive displacement pumps, the video is right here. If you were studying positive displacement pumps in rotatory and reciprocal, are also included here. Centrifugal pumps, which is a very important topic in this course, you have it right here.